Hi, everyone. Hey, let's get ourselves ready for the next exam. Let's look over some stuff for Chem 6, the Introduction to Chemistry course, and specifically the sample test. So let's see, I got the sample test here. So I was looking at it earlier. Let's scroll back to the top of the page. Here's a sample test for exam 4, although in the class I'm substitute teaching for, it's exam 3. More to the point, this is the exam about stoichiometry, about converting grams into moles, doing calculations for reactions. We're also doing energy calculations. We got Gibbs free energy, delta G here, the heat of reaction, delta H, entropy, delta S, those topics. Okay, so I don't have time in this one video to go over the entire sample test. We'll do some key problems here, and I'll do a sampling of a whole bunch of these so that overall we should cover the major topics. And just be aware that you get credit for showing your work. And even if you can't finish it or you have a couple of mistakes, you can get partial credit. So show your work and don't freak out by the length of this exam. This exam is just covering all the possible questions that could show up on the exam, but not all of them will. I'm going to change the numbers, but I'll keep some of the wording the same, and I will make it shorter. This practice test is actually longer than the real thing. Okay. Let's take a look at some of these. Let's do the third one here. Third one actually has the ideas of the first two problems. So let's come on, work with me, Zoom. There we go. Here. Good. Pencil. Okay. So question number 3 asks, hey, a sample of ammonia, NH3, has a mass of 56.6 grams. Sample just means a collection. We just have this in a lab, probably in a flask somewhere, some type of container, and we want to know how many molecules are in this sample. Okay, try using unit conversion dimensional analysis. So what do we want? Molecules. So put that over here on the right side. And it's helpful to identify specifically what molecules, NH3 molecules. So we're trying to find out how many molecules of NH3 do we have? Well, what do we know? We know that we start with 56.6 grams of NH3. Okay, so that's what we're given. Put it over here on the left side. And now we have to find conversion factors, something that can cancel out this grams and change it into the units of molecules. So then you have to hunt around for a conversion factor. Good place to hunt around is the top of the exam. There'll be a listing of equations and data. You don't have to have these memorized. This section is going to appear at the top of your exam. Also, you get the periodic table. And it might include some other things as well. So take a look on Canvas for an update on that. The sample test listed online will tell you what's going to be on your next exam. Okay, but at a minimum, you got these. You got converting Celsius to Kelvin. You got the free energy equation. You got Avogadro's number. What's this all about? Avogadro's number is the number of molecules in 1 mole. Ooh. So this number is a conversion factor that switches between molecules and mole. Well, we want molecules. So if we can get the moles, like if we find out how many moles are here, that's how you solve the problem. So in other words, we need a conversion factor right here that can cancel out the grams and change them into moles. Moles over grams, or grams over moles. And hopefully after doing the homework and seeing some of the videos, hopefully you recognize this grams per mole as the units for molar mass. sometimes called molecular weight or formula weight. And how do you get that conversion factor? You go to the periodic table and add up the weights of the atoms that make up your molecule. So we make up the molecule NH3. Let's go look at the periodic table. You don't have to memorize the periodic table. You get this on the exam. It may not look exactly like this, or it might. All periodic tables have common information. So what are we trying to do? Trying to find the molar mass of NH3. And so it's got one nitrogen. And so the weight of nitrogen is 14.0067 grams per mole. Meaning if you have Avogadro's number of nitrogen atoms, they will weigh 14.0067 grams. That's the power of Avogadro's number in the periodic table. We got 3 H's. How much does 1 H weigh? 1.0079 grams per mole. Okay, so 3 times 1, point this, 14, add them together, and put in your calculator, and you should get 17.0304 grams per mole. 17.0304 grams per mole. That's our conversion factor. Okay, so the number was the molar mass of NH3 using the periodic table is 17.0304 grams per mole. Okay, so 56.6, do we multiply by this number or do we divide? Well, you multiply or divide so that the units will cancel. Whoops, that's a 1. The number kind of goes with the numerator. So the 17 goes with the G, and on the bottom there's 1 mole. So the G is actually down here. So you have to keep the G, the numerator part, with the number part. 17.0304 goes down here. And it turns out we're going to divide. You have to divide so that the grams will cancel out. And up on top, yeah, if you have 1 mole of NH3, they will weigh 17.0304 grams. Nice. But we're trying to get the molecules. We're in moles, so now we want to cancel out the moles and change them into molecules. Well, that's Avogadro's number. That's the conversion factor we need now. In 1 mole, there are 6.02 times 10 to the 23rd molecules. And the moles cancel out. So what do? You earned all the points by showing this work, except for one more point to go. I don't know, is this a 5-point question? You've earned 4 points by correctly setting up the problem, using and finding the correct conversion factors. Now you just have to do the math, and that's not chemistry, so it's only worth 1 point. What do? You multiply 56.6 times 1 times 6.02 times 10 to the 23rd, and you divide that by 17.0304. And let's see, if I round off, I'm looking at the answer key that helps speed up the math. And in the answer key, I rounded off to 1 sig fig. That's not right. So let's do this for real. So 56.6 times 1 times 6.02 times 10 to the 23rd power divided by 17.0304. And I go, oh, I see. It does go off to, rounds off to 2, but where's my pen? We got 3 significant figures here. That 1 is an exact number, doesn't count towards sig figs. There's 6 sig figs here and 3 here. That's an exact number. So 3 sig figs should be my answer. And I got 2.00. The next digit on my calculator is a 0. So the 3 significant figures, it is 2.00 times 10 to the 24 molecules of NH3. Nice. Okay, what do we got next? Number 5, I thought I would do next. Use the following chemical equation, the answer parts A through C below. Here's the chemical equation, but warning, it's not balanced. Okay, that's part A. You'll get points for doing that. So let's go ahead and balance it. So there's 2 main ideas or 2 tips, advice when you're balancing equations. 1, don't change the subscripts. So you can't change this 3, you can't change that 2, and so forth. That's out of bounds. That's changing the recipe. You can't do that. Second tip is save the simplest for last. The simplest molecule is the one that has the fewest elements in it, and it's the least complicated. That's this one right here. AgCl is the least complicated, right? This one's not too bad. There's only 2 types of elements here, Mg and Cl, but there's a subscript 2. This doesn't have it. There's 3 elements in this one, AgNO3, and there's parentheses over here. That's complicated. So you can balance the equation more quickly if you save the simplest for last. Don't balance Ag, don't balance Cl. Go after the Mg, the N, or the O first. And it doesn't matter which one you do, but save AgCl for last. Let's do Mg. So on the right-hand side, I see 1 Mg. On the left, 1 Mg. Ooh, it's balanced already. All right, how about the nitrogen? Well, it's 2 nitrogens, right? 2 times what's inside the parentheses. So there's 2 N's here, none there. A total of 2 nitrogens over here, but on the left side, there's only 1. So we have to put a big 2 in front so that now we have 2 N's. Oxygen, you're next. 2 times 3 is 6. So there's a total of 6 oxygens over here. And then 2 times 3 is also 6. 6 oxygens were balanced. Cool, the Mg, we didn't mess that up. Yeah, 1 Mg on both sides. So now let's look at Ag. Well, there's 2 Ags here, so we need a 2 here. And there's 2 chlorines, and now there's 2 chlorines. We are now balanced. Yay. Okay, we did that part. Also included in part A is how many moles of AgCl3, this molecule, can be produced from 5 moles of this molecule. Some of you can understand the balanced chemical equation and do this in your head, but if you miss it and you don't show me any work, you don't get any credit. So it's best to show me some work. So try dimensional analysis. So what do you want? I want moles of AgCl. That's what I want, some number here. What am I given? So check the question for any digits. Oh, here's a 5. So that's going to go on the left side. 5 what? Moles of MgCl2. Okay. Found, yeah, this is what I want, moles of AgCl. What am I given? 5 moles of MgCl2. Third step, find conversion factors. Change moles to moles. Wait, the units already match. We need to change this molecule, MgCl2, into a different molecule, AgCl. I know, it's kind of weird. We need a conversion factor that changes one molecule into another, and that's the balance equation. The balance equation says every one of these will make 2 of these. 1 mole of this will help create 2 moles of this one. And so what do we put down the bottom? We want to cancel out the moles of MgCl, right? So 5 moles of MgCl2 is what we start with. And the balance equation says for every 1 mole of MgCl2, you can produce 2 moles of AgCl. So just use the numbers in front of the balance equation, the ones we found by balancing it. There's an invisible 1 over here. And now we have our conversion factors. The moles of MgCl2 cancel out, and we're left with the units that we want, moles of AgCl. And then just do the math. 5 times 2 is 10. 10 divided by 1 is still 10. That's the answer. Cool. Part B, how many grams of AgNO3? So what do we want? We want grams of AgNO3. That's what we want. What are we given? Look for a digit. Here, 25, that's the digit. What are the units? Grams of AgCl. Okay. What do we need to do? We need to convert the grams to grams. Wait, that's a match. The molecules don't match. AgCl doesn't match AgNO3. You have to change or convert the molecules. And the way you do it is through a balance equation. The problem, though, is the balance equation has units of moles, not grams. So what we first have to do, so the objective is to realize that, hey, what we got? We're trying to get the AgNO3. So if you end up with 2 moles, there we go. Man, I'm really messing up this equation. Let's rewrite it down here. So the balance equation says that 1 MgCl2 reacts with 2 moles of AgNO3 to produce 2 moles of AgCl and 1 mole of MgNO3, magnesium nitrate. Okay, the balance equation says, okay, 25 grams, that must equal some number of moles. And the equation says for every 2 moles that you make of AgCl, for every 2 moles you make, you must have had 2 moles of AgNO3, the same number of moles. Well, then how many moles of this do we have? Because that must equal the number of moles of this. Oh, wait, we don't want moles, we want grams. Okay, so got to get out of grams, convert in the moles, so we can change molecules in the molecules using the balance equation. This is grams per mole. That's the molar mass again. For this molecule, AgCl. Silver chloride is AgCl. So scroll down a little bit. Down here is Ag. Ag weighs 107.8682 grams for every mole. And chlorine, it's off to the right a little bit. Here it is. Chlorine, 1 chlorine atom weighs 35.4527 grams for every mole. Add those up, and you get 143 and change. Okay. So the molar mass of AgCl is 143.3709, or is that a 2? I think that's a 2. Grams for every mole. And again, we want to cancel out the grams. That's why the grams are at the bottom with the rest of the number, 143.3209. And that converts the grams of silver chloride into moles of silver chloride. Cancel out the grams, cancel out the grams. And then the chemical equation says, well, we want to cancel out the moles of AgCl. Want these to match, cross cancel. So what is this? It's right here. The balance equation says every time you have 2 moles of AgNO3, sorry, it's right here. 2 moles of AgCl, there it is, there's the match. You're gonna make 2 moles of this one, 2 moles of AgNO3. But you want grams of AgNO3. So get out of moles and back into grams of AgNO3. Every 1 mole of AgNO3 weighs as much as all these atoms do when you add them together. So we're trying to find the molar mass of AgNO3 So 1 silver weighs 107.8682. Nitrogen weighs 14.0067. 3 oxygens will be 3 times 15.9994. And I got 169. When you add those up, add up the weights of all those atoms, I got 169.8731 grams for every 1 mole. Cool. Okay, and then you got most of your points right there. Lots of partial credit. To get the final 1 point, do the math. 25 times 1 is 25, times 2 is 50, and then 50 times 169.8731. I didn't show that on the answer key. Take that answer, divide by 143.3209, hit equals on your calculator, and then divide it by 2. And then you should get to 3 significant figures, or maybe 2. There's only 2 sig figs here. Yeah, 25 grams. We should have only 2 sig figs in our answer. So it looks like it's gonna be 30 grams of silver nitrate. Okay, and then we got grams to grams. That's another similar calculation. You can take a look at the answer key for how to set that up and solve that one. But it's done the same way. It's gonna look very similar to this conversion. You're going to change grams to moles with molar mass. That's what we did here. Use the chemical equation to change the molecules. And then finally, the last step is get out of moles and back into grams with the molar mass of the other molecule. Okay, this one is a little different. The question reads, phosphoric acid can be prepared by reaction of sulfuric acid. So how do we tell what an acid is? The H usually starts the chemical formula. Oh, there's an H over here too. Yeah, but phosphate, if you remember your polyatomic ions, phosphate has a P in it, PO4, 3 minus is phosphate. Sulfate is SO4, 2 minus. Hey, this has a sulfate in it. H, that's sulfuric acid, it's right here. And then you react with phosphate rock, the nickname for calcium phosphate. It's an ore. You can actually go find it out in the field somewhere, I guess. Dig it out of the ground. Calcium phosphate, treat with sulfuric acid, you make this calcium sulfate, and you also make phosphoric acid. Okay, it's an acid because, well, you can tell it's an acid because the H leads the chemical formula. That's what these words are trying to express here in the chemical equation. All right, the equation is not balanced again. I'm reading the question and it's not asking me to balance it. Maybe I can get away with not balancing it. Let's find out. Part A, suppose the reaction is carried out starting with 103 grams of the first compound and 75 grams of the second. How many grams of phosphoric acid could be formed? We need to balance this. So I see 2 problems. One, I need the recipe. I need to know how many molecules of calcium phosphate react with sulfuric acid. Second thing is I'm in grams and the chemical equation has units of moles. So I'm going to have to convert grams to moles with the molar mass. All right, so let's begin by balancing this. Let's clean up a little bit too. Whoops, let's delete that. It's a little better. So let's squeeze in our coefficients. Let's balance this. So save the simplest for last. Nothing's jump out at me except for this one. This has parentheses. That's definitely complicated. This one has 3 elements, 3 elements, 3 elements. Yeah, they're all equally complicated. This one doesn't have as many subscripts. There's only a 4 here. This one has a 3 and a 4. So maybe this one's the most simple looking. So I'm going to save this one for last, which means I'm going to balance hydrogen, phosphorus, or oxygen. Let's go after hydrogen. Okay, on the right-hand side, we have 3 of them, 3 H's. Left-hand side, only see 2. Ooh, so how do you get these to match? Try crisscrossing. Take this 3 and multiply it over here. Take that 2 and multiply it over here. Yeah, now you have 6. 6 H's, 2 times 3. And 3 times 2 is also 6. Okay, the hydrogens are now balanced. Let's balance phosphorus. Well, there's 2 phosphoruses. The big 2 times the P. Yeah, there's 2 P's on the left. I'll say it's my right. 2 phosphorus on my right. Over here, the parentheses, 2 times P. Yeah, phosphorus, P is balanced. All right, let's do the oxygens. Okay, 2 times 4 is 8. There's 8 oxygens here, and another 4 makes 12. There's 12 oxygens on the right-hand side. There's a 3 times 4 is also 12, and a 2 times 4 is 8. That's 20 over here, darn it. So do we change this number to get more oxygens, or we put a number here? It's not clear to me. I think I want to put a number here, but you know what, to help, let's balance the calcium. And I see that there's 3 on this side, and I need 3 over here. I know I kind of cheated. I didn't like the option of trying to balance oxygen. It looked too complicated, so I jumped over to another element. And now let's just check. How many oxygens over here now? Now I got 12 here, and I have 8. There's 20 over here now. Sweet. There are 8 here on the left, plus another 12 is also 20. Oxygen's balanced. How's the sulfur look? 3 times S and 3 times S. We are all balanced. Okay, it's nice and balanced now. Cool. Okay, so how many grams of sulfuric, what is this, phosphoric acid, H3PO4, can we make? Well, it depends on which one of these runs out first. 103 looks like you have more of this than that, so maybe you run out of 75 grams first. Ooh, but wait, there's more atoms here. This molecule weighs more. If you have 1 mole of this, it's already going to weigh more. So maybe you don't have as many molecules. And also, the balance equation says you need 3 of these molecules with every one. So there's a lot of things happening here. You can't just look at it and predict and say, oh, I think 103 is the limiting reagent or 75 is the limiting reagent. No, you have to just try it out. Remember, the limiting reagent is the one, this one or that one, that runs out first. How do you know? You just got to try it. So we got to do dimensional analysis twice. Okay, so what do we want? We want grams of H3PO4. And let's start with this one. So found what I want, grams of H3PO4. What do we have? Look for digits. There's 103 and there's 75. So we're going to do the math twice. Start with the 103 of what? It's grams of the calcium phosphate. And I need to change grams to grams. Oh wait, that's a match. Now I have to change this molecule, calcium phosphate, into a different molecule, phosphoric acid. The way to change a molecule to another one is use the balance equation, but this is in units of moles. The recipe says you need 1 mole of calcium phosphate to make 2 moles of phosphoric acid. So that's how you convert between the molecules, but first you have to get the units of moles. So we need to cancel out this gram and change it to moles. We need the molar mass of this molecule. Grams per mole is molar mass. So go add up the weight of 3 calciums, 2 phosphoruses, and 8 oxygen atoms, right? Bounce over here to the periodic table. Calcium weighs 40 and a little bit more. Phosphorus is 30.9738. Oxygen is 15.994. Add those up. And what I got was, this is number 6. 310 grams and 18, so I rounded off, grams for every 1 mole of this molecule. We got to get out of this molecule and get into the molecule we want, phosphoric acid. What's our conversion factor? Comes from the balance equation. Calcium phosphate's over here. It's 1 mole. 1 mole. Phosphoric is here. There's a 2 in front, so put a 2 in front here. 1 mole of calcium phosphate helps make 2 moles of phosphoric acid. And now my moles of that molecule cancel out. We're in the correct molecule, but not the correct unit. One more conversion factor, get out of moles and into grams of the H3PO4 molecule. And to do that, what's the number here? Go add up 3 hydrogens, 1 phosphorus, and 4 oxygens. And I got 97.994 grams. And now our moles cancel out. Good, these are the units, grams, phosphoric acid, that's what we wanted. Nice. In your calculator, multiply 103 times 1 times 2 times 97.994 divided by, well, these are ones, so divide by 310.18. And I got the 3 sig figs. Yeah, we started with 103, 3 significant figures. I got 65.1 grams. Okay, so if we run out of calcium phosphate first, we can make 65.1 grams of the product. If all 103 grams react, 65.1 grams is the answer. Then you have to start all over with the 75. 75.0 grams of H2SO4, right? 75 grams of H2SO4. And we're going to do a very similar calculation, trying to figure out how many grams of H3O4 are we going to make. Well, let's do this. Let's close that out. There we go, more space. Okay, same deal. First, it's molar mass. You divide by it. So grams over moles, because we want the grams to cancel. But now we need the molar mass of sulfuric acid. So use the periodic table to weigh the weights of 2 hydrogens, 1 sulfur, 4 oxygens. And I got 98.086 every 1 mole of H2SO4. Grams cancels out, but now we got the wrong molecule. So cancel out moles of H2SO4 and change them into moles of H3PO4. That's what we want to do. Cancel out this molecule, make it this molecule. And the balance equation has the conversion factor. I got H2SO4 on the bottom. Yeah, there's a 3 in front of that one. It takes 3 moles of H2SO4 to help make, well, there's a 2 in front of phosphoric acid, to make 2 moles of phosphoric acid. And then finally, change the moles back into grams with molar mass. Moles goes on the bottom so it can cancel out. Grams goes on top of H3PO4. Hey, that's this number up here. This conversion factor, and that one exactly matches, 97.994. Good, one more point. No, actually this one, we still have to answer the question. So there's more than 1 point at stake here. So hopefully get your numbers correctly calculated. 75 times 1 times 2 times 97.994. put that in the memory of your calculator, separately calculate 98.03 times 3, and then the top number divided by the bottom number will give you the answer, and I got 50.0. The 3 significant figures. And so now what is the real answer when someone in the lab mixes 103 grams of calcium phosphate with 75 grams of sulfuric? Well, the sulfuric can only make 50 grams before it runs out. This one, the H2SO4, this molecule is limiting. It limits how much product we can make. It's the limiting reagent, or it's limiting the reaction. 75 grams can only produce 50 grams of the product, and then you're out of sulfuric acid. If you had more sulfuric acid, then you can convert the 103 grams to 65. We just didn't have enough. So there's the amount. That's the answer. The smaller amount between 65.1 and 50 is the correct answer, the smaller one. We shouldn't use the word actual. We should say should form, could form. Okay, so theoretically, in a perfect world, all 75 grams should be converted to 50 grams of phosphoric acid. But you know what? In the lab, life happens. We had some spilling. Maybe we stopped the reaction too soon. Maybe when we filtered it, it was kind of cloudy and didn't filter very well. Actually, this is not a solid. That'll make it more difficult to filter. Anyways, there are problems. And someone actually only got 5.5 grams. They did a terrible job. Now the question is, what's the percent yield? Well, they should have got 50. They only got 5.5. So divide the two and change it to a percentage. That's the percent yield. And if you can't remember which one goes on top or which one do you divide by, try them both. Let's round off this to 5 because the math is easier. 50 divided by 5 is 10. Change it to percent, that's 1,000%. Wait, did they get 1,000% of what they are supposed to? No. They didn't even get 50, they didn't get 100%. 50% is 100%. They only got 5. They got much less. Okay, so that's the kind of logic I use to try and help me remember some equations. Percent yield's like telling us how much we actually got, and we did not do very well. We didn't get 100% of what we should have. We got much less. So put the smaller number on top. Those are both in grams. Multiply it times 100. That's percent yield, if you allow me to abbreviate it this way, percent yield. The actual divided by the theoretical is the actual equation, times 100. And now 5.5 divided by 50, times 100 is 11%. 2 sig figs because of the 5.5. That's the percent yield. Cool. Ooh, we actually tackled quite a few problems already. Okay, let's look at some others. All right, number 10 on the sample test is, hey, we're changing gears away from stoichiometry, calculations for chemical reactions. And now we're gonna look at reversible reactions or equilibrium. So this asks us to calculate the equilibrium constant for the reaction below. When at equilibrium, the following concentration amounts are, and then he lists all the quantities. Okay, what does it want? The equilibrium constant. That's symbolized with a capital letter K. And the way you calculate it is you put the concentration of the products up on top divided by the concentration of the reactants. And if any of these show up with a solid or a liquid, they don't count. So no solids or liquids in your calculation. Okay, so we'll answer letter B in a minute. I'm just going to use this space. So what are my products? Well, there's the KNO3 that's aqueous, and it's got a 3 in front. Remember, you have to raise it to the power of the coefficient. So what's my KO3 quantity? It's aqueous, so it does count. It's not a solid or a liquid. It's aqueous. Here it is, KNO3, potassium nitrate. It's 0.44 molar. So 0.44. And then you got to use this 3 as the exponent. What other product we have? We have MnO2. Ooh, red flag. It's a solid. Don't count it. Aqueous, yep, you have to count it, and there's a 3 in front. So how much KOH do we have? Potassium hydroxide, 0.32, and then we have to use this 3 over here. You have to raise it to the 3rd power. Those are all my products. Divide them by our reactants. So first one's water. Ooh, it's a liquid. Don't count it. Doesn't show up in the equilibrium expression. This one's aqueous, so it counts, and there's a 2. So remember, it's square your number. Potassium permanganate, where are you? Oh, it's right here. It's 0.22, and then we got to square it. So let's square it right there. The other reactant is also aqueous, so it counts. It's KNO2, potassium nitrite. Potassium nitrite, you're right here, and the number is 0.54. And there's a 3 in front, so raise it to the 3rd power. Cool. Got a lot of partial credit right there. Now all we have to do is crank it out in a calculator to get full credit. So if you do that, so you might have to jot a few numbers, right? So if you can't find the exponent function, you should. It'll be the little caret. So you put 0.44, little exponent or caret 3. Or you can say 0.44 times 0.44 times 0.44. That's also 0.44 cubed. Yeah. Okay, and you multiply times this, divided by those, and you pay attention to the exponents, you should get to 2 sig fig 0.37. And we did it. That's the equilibrium constant. That's what K is equal to. Cool. Letter B, under the reaction conditions above, so these equilibrium concentrations, are reactants or products favored? So if the products are favored, this is a big number and that's a small number, which means K is larger than 1. Not if, how about when? When products are favored. So does a reaction tend to make more products? If K is less than 1, then it's a reactants that the reaction prefers. And so this number 0.37 is less than 1. So reactants are favored. At equilibrium, it tends to have more reactants than products. 0.37 is less than 1. Not a very good reaction, right? Most reactions you want to make products. This one doesn't care to. Number 11, another equilibrium reaction. Okay, answer the following questions regarding the equilibrium reaction shown. Okay, we got the reaction there. If the concentration of this thing is going to increase, how will the concentration of this molecule change? Okay, this is actually asking about your understanding of Le Chatelier's principle, that balancing act. So the way I kind of imagine these are people, I don't know, not people, but personalities, I don't know. Nature says, hey, got everything nice and balanced. Sometimes these reactants become products. Sometimes the products go back to reactants, and we have nature, Mother Nature's balancing point. There's some quantity on either side. That's an equilibrium reaction, a reversible reaction. And then we mess it up. we come and dump in, we add some of this molecule. And then Mother Nature says, whoa, 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 hey, I had things balanced, you messed it all up. Let's fix it. What can we do to get rid of the extra molecules that you just added? Well, react them away. Let us shift to the right and have these two things make more of the product. And as you react them, they decrease and you make more of this one. And so this molecule is going to increase. Yeah. Do you remember the little 2 tanks of liquid? Right? So we fill this tank with water and it raises the same height over here. And then what this is saying, hey, what if you dump in more reactants, dump in more liquid over here? Well, temporarily the reactant side's too high, but then the water will flow to the right. Yeah, it shifts to the right. And then afterwards, this side will raise up, this side will lower. Where's my eraser? Until they're equal again. And overall, this side will have increased some and the right side will have increased some. Cool. That's what I mean by shifting to the right. Okay, start all over and say, okay, we're going to increase this. What becomes of this number? Sorry, what becomes of that molecule? Well, it's still going to shift to the right because Mother Nature doesn't want this extra molecule sitting around. It's like, get rid of them. So react them away. These two molecules have to combine to form new products. And doing so is going to decrease the quantity of NH3. This is going to decrease. If we added more of this, and so Mother Nature says, okay, let's shift to the right to get rid of the extra, and I'll sacrifice a little NH3 to get rid of the extras you just added. And as these reactants change in products, then the amount of NH3, the concentration of NH3 decreases. Okay, what's next? Start all over, same equilibrium, but we're going to add in more NH3. Add more NH3. How's the concentration of this molecule change? Well, actually, same phenomenon. We're adding more reactants. Mother Nature says, whoa, get rid of the extras by reacting them, changing them in the products. And as you shift to the right, we're going to make more of this, make more products. How will the concentration of this molecule change? Well, if we add more NH3, it shifts to the right and uses this up. So that quantity is going to decrease. This one increases. Yeah. Cool. Next question, not shown in the equilibrium reaction is the fact that an acid is required to catalyze the reaction. So at room temperature, normal amounts, the reaction is too slow. So whoever sets this up says, well, let's add a little acid. Where's the acid in the balance equation? It's not a reactant or a product, it's a catalyst, something that speeds up a reaction, but doesn't get used up. It's not going to be a reactant, and it's not a product being produced. It's something you add. It's special, it just speeds up the reaction without being used up. And so if you add more acid, well, the reaction will go faster because there's more catalyst, but how will the concentration of this molecule change? Turns out, well, the catalyst makes the forward reaction go really fast, so this might start to go down, but the catalyst also speeds up the reverse reaction, so products more quickly become reactants. So this might go up. Wait, it can't do both. Yeah, it's just going to go faster forward and faster in reverse, and this will have no change. The catalyst doesn't change the equilibrium. It speeds up the forward and the reverse reaction equally, and you're just maintaining equilibrium. It's at the balancing point. How will the concentration of the molecule? Same idea, it doesn't change. Both the forward and the reverse reactions speed up at the same rates, so there's no net overall change to any of the molecules. Excuse me. All right, little change here. Answer the following questions regarding the energy diagrams. Which one's the fastest? Okay, so this requires that you understand what the energy diagram is. It's an energy diagram, so we have some form of energy here. It might be delta G or it might be delta H. Those are the two forms of energy we've discussed in this unit. On the x-axis, it's sort of like time, but it doesn't have units of seconds, hours, millennia. Some reactions are really slow, could be years. It just has a generic label of reaction progress. You're going from reactants, that's some energy value, to products, some other value, maybe it's lower. That's what happens with time. The reaction just goes forward, changing reactants to products. How fast depends on how quickly it can get over the activation energy, right? So the distance from where you start to the top of the nearest hill on the right is the activation energy, E sub act. It's the amount of energy it takes to get the reaction going, to get it started. So reactants going to products needs to go over this hill. Reactants going to products, ooh, a smaller hill, that'll be easier. So comparing A versus B, B is faster. For C, you need to get up this hill, and then you also have to get up this one. So overall, you need to climb 2 hills about this height. That kind of looks like the same there. But with this one, you need to get over this hill, and then you go way down here and need to get over that one. It looks pretty close. I think if you get over this hill, you can just get in your wagon and just ride all the way down. The speed, that's how I imagine it. Or you're a mountain climber and it takes a lot of energy to climb this hill, but then you can just jog down here and just let your momentum carry you up this hill and down the other side. So this has the smallest activation energy. Smallest activation energy symbolizes E sub act. That makes the fastest, reaction D. Cool. Next question. If the y-axis represents a change in enthalpy, also known as the heat of reaction, that's nice to know. How much heat does the reaction put out? Or does it chill off? Does it absorb heat? Which reactions are endothermic? Okay, so y-axis is delta H, going up in this direction. These are all delta H, increasing that way. Okay, if it's endothermic, then the reaction is sucking up the energy, the heat energy. The surroundings are going to get colder, but the energy of the system of the reaction is going to increase. That means you're going to start with reactants and climb up the products. Reactants are going to gain energy, this much energy. That's the change in heat. Endothermic means delta H is positive. And if you go from a low value to a high value, yeah, the change in H increased. It became higher in value. It is a positive increase. So going from here, did you go up in it? No, this one went down. This one's exothermic. The reactants lost energy. Energy exited from them. So now the overall system has a lower energy. It lost energy. Same is true here. This went down. This is exothermic. Ooh, start low, end high. Here we go. Here's an endothermic reaction. So letter C is endothermic. And then D, nope, you start at high and you end low. That's exothermic. So where you start and where you ultimately end up, that's the product. This is called an intermediate. So if you could watch the reaction take place, the reactants change into some other molecules called intermediates, short-lived products, but they're not the final products. They're reactants again that change into the final products. So that's why there's two hills here. Doesn't really matter. If you're trying to decide is this exo or endothermic, compare the starting and the ending points. Is it an overall decrease? Delta H is negative, they go down. Or is it an overall increase? Start to finish, no, we increase in energy. Delta H is positive, it increased. That one's endothermic. Reaction C. Here's C again. Energy diagram C represents a sequence of two reactions. The products of the first reaction serves as the reactants of the second. Yeah, we just kind of went over that, sorry. Which reaction has a larger activation energy? Okay, so starting here and going to there has that much activation energy. Starting here and going to there has less. The first reaction has a larger activation energy. We measure activation energy from the valley before the hill. Again, think of the mountain climber. Someone brings in a person by helicopter, drops them off on this valley, say, okay, climb up the hill. Well, let's do this. Let's put identical twins. The helicopter drops one twin here, the other twin here, and said, okay, it's a race to the top of your nearest hill. Go! This twin, it's going to take longer to get up here than this twin. It's going to be easier to climb the second hill. It's going to be faster. Yeah, this one's faster, but the question was actually larger activation energy. So just look at the size of the hill. Sorry, I'm overanalyzing. Larger activation energy, larger hill. First one. Energy diagram B, if the temperatures increase, will the reaction occur faster or slower? Doesn't matter what reaction you're talking about. B, A, C, or D. What does temperature do to the speed of the reaction? Well, temperature is actually a measure of kinetic energy for your molecules. A low temperature, they're chilling, they're cold, they're hanging out, they're not moving. Higher temperature, they're moving. Hotter temperatures, they're moving a lot faster. And when they collide, they're going to hit a lot harder, allowing the reaction to go. If they're cold, they might glancingly bump off each other and not get over the top of the activation energy. So at high temperatures, all reactions speed up or go faster. So sorry, that was a little deceiving, thinking something special about energy diagram B. No, increase the temperature, that'll help every reaction to speed up. For energy diagram A, what is the enthalpy change for the reaction? Okay, now you actually have units over here. We actually want to make a measurement. And it says assume the units are kilocalories. So at the top here, there's 70 kilocalories. At the bottom, it's 25 kilocalories. What's the enthalpy change? Enthalpy change is where you start. Looks like it's starting at, what is this, 25, 30, 35, 40, 45, 50. Yes, you start at 35 and you end up at 25. So the change is you start at 35 and you went down to 25, although you should be doing final minus initial. You should say 25 minus 35 because that's a negative 10. Okay, if you do 35 minus 25 and you got 10, when we report delta H, realize you're going down in energy. Is this endo or exothermic? You're releasing, you're the fire, be the fire, and release the energy and turn to ashes as all your energy exits because you're exothermic. And exothermic means you're losing energy, it's negative. So what's the enthalpy change? You're decreasing, so it has to be a negative 10. And if you want your math to produce the minus sign, that means you have to take your final energy, 25, and subtract it from your initial so that you can automatically get that negative 10 in there. then negative sign. Or you can just say 35 minus 25 is 10, and oh, my direction's going down, therefore there must be a minus sign. It's exothermic. What's the reaction's activation energy? Okay, that's where you start, 35, and where do you end up? You end up at 70. And so the final, the activation energy, is equal to final minus initial again, 70 minus 35. End up at 70, right, top of the hill. You start at 35. That's also 35. What's the sign? Well, you started low and you ended high, you went up. It was an increase. It's a positive 35 kilocalories. Ooh, that's your activation energy. On the exam, this will really help if you label it, circle it, so I can find it more easily. If you don't, that's okay. I'll just hunt around a little bit and see if I can figure it out. Of course, if it's too messy and I can't, well, then I may not be able to give you all the points you deserve. So try to be organized without wasting too much time, right? Don't write me a paragraph about explaining it. No, don't need to do that. Ooh, we finished those. I think this is our last column. What else we got? Here, number 13. It's a multiple choice problem. So there will be some multiple choice formats on the exam. So I thought I'd throw some in there. I don't know if I like this one. I have a test bank that suggests some problems. So I threw this one on the sample test just to get us thinking. It's not my favorite. A chemical reaction is most likely to be spontaneous if it is accompanied by and then different amounts of entropy and energy, or none of these. Okay, so what do we got? Well, what does it mean to be spontaneous? Or how can we tell if something's spontaneous? Well, for most people, a spontaneous reaction is a negative thing. That's how I remember it. Delta G is negative for something to be spontaneous. Okay, and we have an equation for delta G. So over here at the top of the exam, you don't have to memorize it. There it is. Delta G equals delta H minus T delta S. And that's actually what we need here. So we'll put over here, delta G equals delta H minus T delta S. This is free energy. This is the enthalpy, or heat of reaction. S, well, T is a temperature in Kelvin. That's important. And this one is entropy, which is the craziness factor. It's the measure of randomness. Okay, so that's the equation we want. We want delta G to be negative. And delta H minus T delta S is what we have. And the possibilities are either increasing energy or lowering energy. Increasing energy or lowering energy. The other one's increasing or decreasing entropy. Ooh, that's delta S. That's entropy. So the energy must be the delta H. Yeah, the heat of reaction, heat energy, that's what it's referring to. So if you have a reaction and it's increasing energy, that means delta H is positive. If the system is increasing energy, that's endothermic. It's gaining heat energy. It's gaining energy. And if it's increasing entropy, it's getting more and more random. That's also positive. Temperature, what's its possible algebraic sign? Is it positive or negative? It's in Kelvin. And it's never negative. It's not negative ever. The lowest you can get is absolute zero, which means there's absolutely no motion of atoms. They're completely devoid of energy. They can't move. Can't get any less energetic than that. No negative Kelvin temperatures. Above that, it can be positive. So temperature is always positive. Okay, so if you want G to be negative, this shouldn't be positive. It should be negative. So let's change this. You want it to be an exothermic or lowering. And the exothermic reaction, it's losing energy, a lowering of energy, making it negative. Good, because that matches delta G. That's what we want. We want this. So let this be negative. And if you increase the randomness, positive. Temperature is always positive. Positive times positive is always positive. If you subtract the positive number, that's the same as adding a negative number. Or in other words, this thing is always going to be negative. And if you add a negative to a negative, it's always going to be negative. Told you I didn't like this. What's this all abstract positive negative business? If you followed that logic, rewind the video and listen to it again, you'll see that if delta H is decreasing, negative, delta H, that's S. Delta S is increasing, but you have to change the sign. That'll always allow delta G to be a negative number. And if it's negative, it's always spontaneous. So that's the answer. Increasing entropy, this one, and this one, but decreasing or lowering energy. So that's letter B. You want to lower the energy and increase the entropy. Hey, let's start over. If you didn't like that, let's try something else. Trial and error and guessing, well, educated guessing. Increasing energy, that means this is a positive number. Well, how about a plus 10? How am I guess a number? Grab your favorite digit. Multiples of 10 are easy to add and subtract, so that's why I grabbed plus 10. You're going to, let's just try letter A. Letter A says increase the energy and increase the entropy. So subtract, well, let's let the temperature to be 100 Kelvin. And if it's increasing entropy, this is also a positive number, maybe 10. Cool. So 100 times 10 is 1,000. A plus 10 and minus 1,000 is equal to negative 990. Hey, it's negative. It's spontaneous. Cool. Yeah, but what if instead of plus 100, we said plus 1,000,000 or plus 10,000? And then we kept temperature at 100 and the S at plus 10. So then we subtract 1,000. And now this is a positive 900. And that's positive, so it's not spontaneous. That's telling us letter A is not the best. It's when is it most likely to be spontaneous? Well, it could be spontaneous, but it also could not be. It may not be. So then try letter B. Well, what if you start all over? Maybe over here. Delta G equals delta H minus T delta S. You want to lower the energy. So let's say it's a negative 10. And then temperature, I'm going to keep it at 100. Delta H, S, delta S is increasing. So maybe it's a plus 10. And then you got minus 10 minus 1,000. Cool. A minus and a minus makes a bigger minus. It's 1,010, and that's always negative. Put in a negative 1,000 minus another 1,000, right? Keep the 110, and now you got a negative 2,000. Okay, that's cool. By changing these numbers, we saw it's sometimes positive, sometimes negative. Bad answer. Change the numbers, it's always negative. This is the right answer. You want negative to be spontaneous. Just another strategy to try and solve that problem. Ooh, okay, 14. For which processes is delta S negative? Okay, so first ground yourself. What does that mean? Well, delta S is the random factor. It increases as things get more random, more disordered. If you make them negative, that means it's less random, more ordered, more organized, more neat, and put in its place. So let's see if these processes, some are reactions, some are not, just physical changes. Are they making the system more ordered and neat and organized or not? Is it getting more crazy? What if you evaporate a mole of this molecule that was originally a liquid? Wait, so you're telling me you had a little beaker of liquid, nice and neat in a nice beaker, and then you heat it up and now the whole room is filled with the molecules of gas. Okay, that's more crazy. That's not more ordered. Okay, what did you do here? You took 5 milliliters and you mixed it with 25 milliliters of water. Wait, you had 5 milliliters in one flask, you had 25 in another, and you mix them together? And now, like, where's this molecule? It's somewhere in there. It was nice and neatly separated. Wait, that's more random. Nope. Compressing 1 mole of neon gas. Okay, so you started with a box of neon gas. The gases are anywhere in the box, and you compressed it. You squeezed it into a smaller box. Ooh, that's a little more neat and organized. The gas molecules are, I have a better idea where they are. They're somewhere in this smaller volume of space. Yeah, that is a little more neat and organized. Am I done? Read the question. It says circle all the correct answers. So there might be more correct answers. Let's find out. Letter D, raising the temperature of 100 grams of copper. You can go to the periodic table, or just know that that's just an atom. 100 grams of these atoms from 275 to 295. Okay, what happens with atoms as you heat them up? It increases their kinetic energy. They go a lot faster. They get a lot more crazy. No, raising the temperature is going to make things more disorganized. What if you grind a large crystal? Wait, you had a nice crystal, a big cube, and you just crushed it in a bunch of tiny little crystals? That's not making things more neat and organized. Okay, what about this last one? It's a reaction. Take 2 of these gases and make 2 plus 2 is, you make 4 gases. So if I know where 1 sulfur is, I got a good idea where the other 3 are, right? So if you have knowledge about the sulfur, there's 3 oxygens attached to it. So you got a good idea where they are. That's not very random. But if you know where this sulfur is, you only know about where 1 oxygen is. The other 2 could be anywhere. It's in a separate molecule. If you increase the number of gases, that increases randomness. Nope, that doesn't work. There's only one answer here. This time, if I ask this question on the exam, maybe there's going to be more. Or the other idea is I could change the question and say, hey, for which one is delta S positive? Okay, so be careful, read the question carefully. Ooh, okay, this is out of order. I wrote a little note, glad I did, saying, Dennis, don't do number 15, do 17 first, because there's something that can be helpful. So we'll go down here to number 17. I think that's the last one. Well, no, 15 is the last one. Let's start with 17. Converting solid ice to liquid water absorbs 1.44 kilocalories per mole. Well, yeah, if you melt some ice, the ice is gonna, absorb that energy. If you put ice on your skin gets colder as the ice absorbs heat energy off of you. And the ice, what does it do with that heat energy? It changes into liquid water. It's absorbing it. Okay, what are the signs and values of delta H? Okay, the heat of reaction, I know this is not a reaction, but is this an endothermic or exothermic process? And B, the ice cube, right? So if you're B, the fire, you're releasing heat energy, you're exothermic. B, the ice cube on someone's skin, you're sucking up the energy, you're a vampire, sucking up, a mosquito maybe. You're absorbing the heat energy. That's positive, that's endothermic. Delta H is a positive value. And what's the value? Well, it's right here. You're absorbing energy, units of calories. For every 1 mole of water, it's going to take 1.44 kilocalories of heat energy. Cool. Okay, so we found the sign plus, and we found the value, 1.44 for delta H. Let's do it for delta S. Well, we can predict the sign. Is this getting more or less crazy, less random? Well, if you know where the water molecule is at the corner, it'll still be there. If it's solid, it's going to vibrate in place, but it's attached to the solid. But in liquid, if there's a water molecule here, come back later, it may have diffused to a different part. It's going to be anywhere. It's more random. So what happens to the sign of delta S as it becomes more random? It becomes more positive. It increases. Okay, what's the number? We got to calculate that. How do we calculate it? Neat trick. Go to the top of the exam and see if you can find an equation with delta S in it. There's only one, the Gibbs free energy equation. So grab that, delta G equals delta H minus T delta S. Yeah, this one right here. Scroll down, we're working on 17. Okay, do some calculations. We're still doing part A. The equation is delta G equals delta H minus T delta S. What do we do with that? What's the value of G? Okay, this is the trick. That's why I want to do 17 before 15, because we need this trick again. What does delta G mean? Delta G means if it's negative, it's spontaneous. Reactants will spontaneously go to products. If you give it a little push, it'll keep going all by itself. If delta G is positive, that means it's not spontaneous. It means reactants do not go to products. Instead, products will change back into reactants. The reverse reaction is true if delta G is positive. Last one, what happens if it's neither negative or positive? It's zero. Well, if it's negative, it goes forward. If it's positive, it goes reverse. If it's exactly zero, you're at equilibrium. Equi with a I. Equilibrium. It's reversible. So when ice is melting the water, what temperature does that happen? 0 degrees Celsius. What's the freezing point of water? 0 degrees Celsius. So technically, as the ice is melting the water, sometimes a little bit of water can refreeze the ice. It's at equilibrium. I know that's not happening, but if you could hold the temperature at 0 degrees, then that's true. At 0 degrees, if you hold the temperature, the reaction can go back and forth. Some ice will melt, some water will freeze if you hold the temperature exactly at 0 degrees. While the ice is melting the liquid, the temperature is at 0. So technically you're at equilibrium, but your warm skin is heating this, adding energy, and it's making the forward reaction go faster. But you're still at 0 degrees. Technically you're at equilibrium or at the equilibrium temperature. You can then say, as this ice is melting, during that time where it's still melting, delta G is 0. That's the trick. So now we have a number we can put in for our equation. What's delta H? It's 1.44 and it's positive. And it's kilocals per mole. What's the temperature? Well, we just said it's right here. It's 0 degrees Celsius. Can I put a 0 here? No, because 0 times delta S is 0. Wait, what if this was negative? Temperature can't be. Wait, this is Kelvin. Yeah. So go back to the top of the exam and find out how to convert Celsius to Kelvin. All you do is you take the Celsius temperature and add 273. So if we're at 0 degrees Celsius, that's equal to 273 Kelvin. Cool. So thank you. Equations at the top of the exam. Okay. T then is equal to 273 Kelvin. Delta S, ooh, that's our X. That's, if you want to use the letter X, you can, if you like doing your algebra that way. Delta S is the unknown number, unknown variable. So do the math. We got a minus sign between these two things. So let's get this to the other side, although we can subtract this number, or add it rather, to cancel it out. So on the left side, then you have 273 times delta S equals a plus 144 calories per mole. Excuse me. And there's a Kelvin here if I want to keep the unit. Now you divide by 273 Kelvin. And then delta S is automatically positive. Well, that's good because that's what we predicted for melting ice. The water is becoming more random. It should be a positive number. And then 144, ooh, that's in kilocalories, so keep the same units. Kilocalorie per mole times Kelvin. And then let me look at the answer key, although probably could grab the calculator just as quickly. Yeah, I definitely could have been faster. I got, well, how many sig figs do we have? We have 3 and 3. Okay, so 3 significant figures. I got 0.00527 kilocalories per mole Kelvin. Yay, that was question A. Letter B. How many kilocalories are required to melt 12.5 grams of ice? Well, try dimensional analysis. What do you want? Kilocalories. Okay. Those are kcals. What are you given? Find some digits. 12.5. What are the units for that? Grams of ice. Okay, so you need to change grams of ice into kcals. Do we have a conversion factor anywhere? Yeah, right here. Kcals per mole. If you had 1 mole of water that was frozen, 1 mole of ice takes 1.44 kilocalories to melt it all. Darn it, why didn't you say we had 12.5 moles? That would have been easier. No, they told us we have grams, so you gotta get out of grams and into moles. What's the chemical formula for ice? It's H2O. So this is molar mass, grams per mole. Go to the periodic table, and 2 hydrogens weigh about 1, an oxygen weighs about 16. This should weigh about 18. If you do the math, it is 18 point. I round it off to 18. Let's get the calculator. Okay, it is hydrogen, oops, 2 times 1.0079. I got the periodic table over here too. 1 oxygen is 15.9994. Add those together. 2 times 1.0079 plus 15.999 and a 4. There it is. 18.0152 grams per mole. 18.0152. That's not a comma, that's a decimal point. Decimal point for every 1 mole. Cool. And then it says for every 1 mole, you need 1.44 kilocalories of heat energy. Nice. Moles cancel, grams cancel. We got our kcals, kilocalories. So 12.5 times 1.44 times 1 divided by 18.0152. We got 3 sig figs here. So 12.5 times 1.44 divided by 18.0152. I got 0.9991. How many sig figs? 3. 0.999 kilocalories. There you go. That's how many kilocalories of heat energy, about one kilocalorie of energy to melt 12.5 grams. Cool. All right, let's do the last one for this video. Question 15. For a particular chemical reaction, delta H is 5.5 kJ. Endothermic or exothermic? It's endothermic, right? This is a positive number, making it endothermic. And this is a negative 25 joules per Kelvin. This getting more or less random? Less random, it's negative, so it's more ordered. And then under what temperature condition is the reaction spontaneous? Spontaneous, that's delta G. And so what we want is delta G equals delta H minus T delta S. So let's find out. We got numbers, let's calculate it. Okay, delta G, I want to know that number. Delta H is a positive 5.5 kilojoules minus temperature. Oh, it wants to know what temperature. Ew. So I need to guess some numbers. That's one way to solve it. And maybe you might want to guess 220, since those are some possible answers. S is a negative 25 joules per Kelvin. Okay, let's get rid of the minus sign. A minus times a minus is a positive. Okay, and then if you want, you start throwing in some numbers for temperature. Maybe the 220, wait, is this real? Can you have a negative temperature in this equation? This temperature has to always be Kelvin. It can never be negative. So it's like, what? No, not a smiley face. Let's get an angry face going. That is just totally wrong. No way. Temperature cannot be negative, below negative. Can't be less than negative 220. What's that all about? Weird. This can only be 0. So absolute 0, that's the smallest number it can get. 0 times 25 is 0 plus 5.5. That's a positive number. It's positive at T equals 0 Kelvin. And delta G has to be negative to be spontaneous. Doesn't work at absolute 0. So now go higher than that. Well, how about 10? How about temperature equals 10 Kelvin? Still pretty chilly. 10 times 25 is 250 joules. It's a positive number. Add that to another positive number. It's still positive. How about take up the temperature up to 1,000 Kelvin? Well, 1,000 times 25 is still a positive number. Plus another positive, it's still positive. This is never going to be negative, not for any temperature. It's never going to be negative at any temperature. And if it's never negative, it's not spontaneous. There you go. Okay, you know what? That was the last one. Cool. I have the answer key on Canvas for all the questions in the sample test. Post your questions on the discussion board and help each other out. And good luck on the next exam.